Welcome to Chibuzor Mathphysics, and I will be taking you through the final examination 2022 May to July 2022. Actually, this is the latest paper for linear algebra 2, and we are going to be looking at this paper. When you look at this paper, you will see that most of the questions contained in this paper we've already handled. So you might need to refer to the previous video so that you will know how to do those questions. So we are going to start. It has 5 sections, and I would like to start with question 5 or session 5 since I have already covered session 1 and up to 4 in the last video. The question number 5, we are going to be stating Cayley-Hamilton theorem and verifying such a theorem, and afterward we are also going to look at the minimal polynomial of an n by n matrix and find the possible minimal polynomial of a 3 by 3 matrix. I remain your friend Augustine Gallagher. Stay with us and enjoy the video. So here is the question number 5, and if you observe, question 5 contains 20 marks. So the first question in this paper, in this question 5, says state without proof the Cayley-Hamilton theorem. State without proof. So let us state without proof Cayley-Hamilton theorem. What did the Hamilton theorem tell us? So let us do that right now. So according to Hamilton theorem, let's take the pen. Sorry for that. Welcome back. Now let us look at Cayley-Hamilton theorem, and according to that theorem, it states that a square matrix, every square matrix, so we are looking at Cayley-Hamilton. So this is Cayley-Hamilton. We're looking at what this theorem states. So according to this theorem, it states that a square matrix satisfies its own characteristics equation. So according to Cayley-Hamilton, it says that a square matrix, when we say square matrix, we mean matrix n by n. So any n by n matrix will satisfy its own characteristics equation. That's exactly what Cayley-Hamilton theorem states. And question number 2 says verify the theorem in A above. to verify the theorem. In A above. In A above, for matrix A, which is given by we have 2, 3, then we have 4, and then 1. This is 2 by 2 matrix. So we are to verify that this is indeed Cayley Hamilton, and that it satisfies the statement that a square matrix satisfies its own characteristics equation. So to do this, let us have a solution. Good. So we are looking at matrix A with the following matrix: 2 by 2 is 3, and then 41. So first of all, we need to find the eigenvalues for this matrix using A minus lambda I. A minus lambda I. This will be equal to 2 minus lambda, then we have 3, 4, then 1 minus lambda. And this must be equal to 0 because we are looking at what is the determinant of this matrix. Since it is 2 by 2, it makes our work easier. So 2 minus lambda multiplied by 1 minus lambda, and minus 4 times 3, in this case is 12. This must be equal to 0. So let us open this. 2 by this will give us 2. 2 by lambda will give us minus 2 lambda. Negative lambda by 1 is simply negative lambda. Negative lambda will be positive lambda squared. Minus 12, this is equal to 0. So here we have 2 minus 3 lambda, because we know minus 2 minus 1 will be minus 3 lambda plus lambda squared is minus 12. This is minus 12, and this is equal to 0. Of course, 2 minus 10 will give us 2 minus 12 will give us minus 10. Rearranging this, we will have lambda squared minus 3 lambda, and then minus 10 is equal to 0. Now, according to by Hamilton, let's have this. By Hamilton theorem, this becomes lambda becomes a squared minus 3a minus 10I must be equal to 0. So the idea is that at the end of the day, this must be equal to 0. Whatever we are going to compute must be equal to 0. And this is our matrix A. We simply need to square this matrix A. If we do that, we will have our A is 2, 4, 3, 1. This is matrix A. Square this matrix minus 3A, 3, 2, 3, then we have 4, 1 minus 10, but now it is 10i, and 10i is simply an identity matrix, and this must give us a 0 matrix. This has to be 0, 0 matrix for it to satisfy Cayley Hamilton theorem. So let us see what is this matrix squared. When we square this matrix, what do we get? You can use your calculator to square this matrix and see what the solution would be. So you can do that. So when we square this matrix, we will get 16. We'll have 9, and then 4. We'll have this is 12. We have 12 and 13. This will be 12 and 13. 12, then we have 13. So this is what we get in matrix A squared minus, let's 3 by this. This will be so this will give us 6, and this will be 9. This will now minus 10 into this. This will give us 10, and this is 0, 0, 10. So let's check if indeed this matrix will be equal to 0. This is 16 minus 6 will be 10. 9 minus 9 in this case is 0. And then 12 minus 12 is 0. 13 minus 3. Let's just confirm that. Yes, so 13 minus 3 here, you will still get 10. So this is what we have, and minus 10, 0, 0, 10. So this is what we have. So this matrix minus this will simply give us 0, 0, 0, 0, 10. 10 minus 10 is 0, 0 minus 0, 0, 0, 0, 0, 0. So here indeed will be 0, 0, 0. This will be 0, 0, 0, 0. Just like what we have here. So indeed, you can say that this matrix satisfies Cayley-Hamilton theorem, because according to Hamilton theorem, a square matrix satisfies its own characteristics equation, and that characteristics equation is that A minus lambda I must be equal to 0. And that's why at the end of our computations, you see where our matrix, the result matrix, is 0, 0 matrix. So indeed, this 2 by 2 matrix satisfies Cayley-Hamilton theorem, and this is how we handle question 1 and 2. So let us now continue with question 3 and 4 in chapter 5. And we are going to be dealing with the minimal polynomial. We are to define what is meant by minimal polynomial of an n by n matrix A over a field F. And after that, we are to find the minimal polynomial of 3 by 3 matrix. We will continue that question in the next video. I remain your friend Galagash. Share and subscribe this video.